ended was looking at some functionality and structure and then talking about some kind of reactivity. And before we start getting into that, I want to double back through some stuff. When we talk about functionality and structure, one of the things that we're looking at is differences in electronegativity causing kind of reaction differences. And that's one of the reasons why we want to be able to look at a bond and identify whether it was ionic, polar covalent, non-polar covalent, all that kind of fun jazz. So if we looked at the HCl bond, hopefully what we would see is that the chlorine is very electronegative, which means it is taking the electrons away from the hydrogen, making the chlorine very partially negative and the hydrogen very partially positive. Okay. This generates a dipole. So we could reference it as a dipole moment, or we could really just kind of think about the chemistry associated with this positives and negatives. Really the biggest deal for me is dealing with those positives and negatives and less the term of going back to the dipole. However, if we go all the way back and talk about our solvents, we encounter issues that shows up with solvents and dipoles as well. Okay, so if we switch this up and look at a new example, let's take a look at water. And if we were to say, look at the Lewis structure for water, we might have something along these lines, right? I don't know why I decided to draw those in red. Go back and draw them in black. Okay, and we could go through and we could establish a dipole within an individual bond. So if we look at that oxygen-hydrogen bond, it is a polar covalent bond. Those electrons are spending most of their time on the oxygen, which makes the oxygen negative and the hydrogen positive. Because it's not an ionic bond, we could go through and say dipoles or show the deltas, saying that these are partially positive and partially negative. What we've established is a dipole on that bond. But one of the things that we're going to be responsible for, particularly as it comes to solvents, is applying that dipole to the molecule. We move out to the molecule is the sum total of all the bonds. So if we go through and look at water, there's another bond. And if we look at that other bond, those electrons are getting drawn equally towards that oxygen, making a partial negative on the oxygen and a partial positive on the hydrogen. Based off of what we are now looking at, should we see a dipole for this molecule? Okay. The oxygen is pulling electrons away from the hydrogens equally. So if we were to look at our drawing here, are the electrons getting pulled any one direction over another? The left oxygen is pulling it rightwards. The right side oxygen is pulling the electrons leftwards. Is there a net dipole?
Yes.
Okay. Where?
Oxygen.
Oxygen's in the middle. Where are the electrons getting pulled in this molecule? Okay. Your hand gesture is good. Do you want to throw in a hand gesture also? Okay. And so this becomes an important distinction that I really want to address based off of what I've been seeing for some people's answers on that dipole quiz. If we look at the way this is drawn, these electrons are getting pulled inwards. Whoosh. There's no net dipole. So if we consider me as the person, okay, if I pulled this direction, but I didn't pull this way, what might happen? You might see my body lean that way, right? Okay. If I pulled this direction, but nothing else, I might see my body pull that way. If I pull both ways equally, what happens to the body? Doesn't move. That's a net zero dipole. So the analysis based off of what we have drawn here would suggest that water has no dipole. And if it has no dipole, that would tend to put it into the non-polar category. No polarity, no dipole. Right? What we've already kind of established and addressed, careful you writing that down makes me very nervous.
So it's not like for every
Non-polar molecules, yes, that's fair. Non-polar molecules will have no net dipole. Yes, that's true. If that's what you're writing, you're okay to write that. Okay? The part that I'm nervous about you writing is saying that water is now a non-polar molecule. Because is water a non-polar molecule? No, it's absolutely a polar molecule. but I just drew it. How could it possibly be a polar molecule if all of those dipoles align exactly as I said? Well, as Annie was suggesting with her hands, I'm being a bit disingenuous with my Lewis drawing. Okay? And this goes all the way back to Unit 1. Lewis drawings do not show shape. You have to add that layer on top of it. So that if I look at the water molecule and say, oh, that's perfectly linear and all that straight jazz, it's not linear. That occupies a bent geometry. And what I should be looking at when I talk about the water molecule is the bent shape. And if I now go through and establish all those partial positives and negatives, I'll get a negative up at the top, and I'll get partial positives down here. Okay? That is a net dipole. Okay? Where is the net dipole, though? And that becomes kind of a harder question. So I want to be able to draw a single arrow saying, this is the direction of my dipole. Okay? Can I say it's only going this direction? One bond is going that direction. I asked for a single arrow to represent my molecule. By drawing that single arrow, I'm only representing the bond, not the molecule. So to evaluate the molecule, what do I have to consider? The sum of all of the bonds. So there's a dipole on that bond. There's a dipole on that bond. So where's the molecule dipole? Okay. The molecule dipole, if we get real fun and exciting, we can bring in mathematics. We'd have to do a little bit of trigonometry behind this. And we could drop in an XY coordinate plane. And if we look at the purple one, it's pulling to the right with roughly that force, and it's pulling upwards with that force. Everybody see that? What's happening on, I called that one, whatever. If we look at the other one, what happens? It's pulling to the left, and it's pulling up. What happens to the dipole left and right on, if we want to call it our x-axis versus our y? Is there a dipole on the x-axis? So that would be this horizontal line. The oxygen is pulling the red hydrogen to the left. The oxygen is pulling the purple hydrogen to the right. Is there a net dipole? Yeah. Okay. The hand gestures when making me move is exactly the same option. I'm pulling with the right, and if I pull to the right, my body moves. That's a dipole. If I now pull with an equal and opposite force, what happens to my body?
Stays there.
Because there is
No net dipole.
no net dipole. So on that x-axis, there is no dipole. Doesn't exist. Right? How about on the y-axis? Yeah, it pulls up. Okay? And now we've got a tricky question. It pulls up with how much force? Okay? That how much gets a little bit hard because we haven't quantified anything, so let's quantify some stuff. Let's say for the purple one, it pulls to the left one and up one. On the red one, it pulls to the left one, up one, right? So on the x-axis, what's our net pull? Well, it's one going one direction, one going the other direction. That's 1 minus 1. That's a zero dipole. How about on the y-axis? I'm pulling up with a force of 1, and I'm pulling up with a force of 1. What's the net force in the upward direction?
2.
They're not additive because they're going the same direction. So what we can do is we can break down every bond dipole, and we can address the geometry of where those things are located to say whether there's a dipole on the overall molecule. So for the sake of water, yeah, there is a net dipole. That net dipole is located squarely on our y-axis, and we can usually just see the arrow going shown straight up, with a little bit of curve if you can't draw straight lines. Kind of makes sense? Okay. What happens if we move to... actually, I'm just going to go to a whiteboard, erase all that. What happens if I move to CH3 positive? Okay, well, if I drew out the Lewis structure for that, hopefully I would see this. And I would have a positive charge on our carbon. I want to know about the net dipole in this molecule, which admittedly this is an odd example, but let's push on it anyway. Okay, is there a net dipole? Why? Okay, that's exactly what I was expecting someone to say, so good job. Bad Mike, bad example. Fine. Let's fix it. We'll make them chlorines. Are they now polar bonds?
I'm thinking about a charge.
I don't care about the charge right now. All I care about is the bonds. Are they now polar bonds?
No.
So they're non-polar bonds? So when I look at the bond between carbon and chlorine, is that ionic? Is that polar covalent? Or is that non-polar covalent? Is carbon or chlorine a metal? No. So it's not ionic. Okay. Are carbon and chlorine the same atoms? No. Is carbon and chlorine carbon and hydrogen? No. Which means not non-polar covalent. Which means that bond is polar covalent. So we could call it polar or polar covalent. I'm fine with either of those terms to describe that individual bond. If we ignore that positive charge, is the molecule polar or non-polar? Okay. Because those are all chlorines, they're all pulling with the exact same force, same electronegativity. Okay? And they're all going to pull their individual directions. And if I did this right, they were all equal length arrows. If we take a look at red and purple, so we're going to kind of arbitrarily pick our axis, x and y. The red pulls down with a force and pulls to the left with a force, right? What does the purple do?
Down and right.
Down with a force and right with a force. What happens to the force on the x-axis? They cancel each other out. Okay, those are both pulled out. Okay? But I've got two pulling down versus one pulling up. What would that suggest? Would that be equal?
Can we cancel out the green one with the purple?
Okay. Can we cancel out the green one with just the purple?
Yeah, the purple down.
Okay. What do you think, Kimball?
I don't think you could because it's two different forces or like two different dipoles.
Okay. And this becomes the fun with trigonometry and all that fun stuff. Okay. These are pulling at a downward angle, which means this downward force is not the same as this upward force because it's pulling down and to the right. Some of that pull to the right means it can't pull down, which therefore means the downward force of this purple cannot equal the upward force of the green. Okay? Well, what if I look at both of those forces? Can they overcome the green? Well, how would I know? What do I got to do?
Count it out.
I got to do actual trigonometry. Yeah, there's the standard good face for that. Yeah, that's just ugly. I don't want to do standard trigonometry to figure all that out. Okay, and full disclosure, I don't want to do it. I might be able to do it, but we definitely don't have enough time in class for me to try and figure it out. Okay, what you end up finding though is that these two downwards equal exactly that one upwards.
Could you do it based on like bond angles
It is bond angles. It's all coming from bond angles because that's the trigonometry looking at how the angles align. You have to address the bond angles behind those. How are they pulling down so that you can figure out the SOHCAHTOA, if you remember all that sign of opposite over adjacent. You have to know all the angles. How do you get the angles? Those come from knowing the bond angles between those. Okay? So officially this is being split in half. This was 120, which means this is 60 and this is 60. Okay, which means that angle is a 60 degree. If it's pulling down with that force, what's the adjacent? Yay, trigonometry, and you would find they all equal out, 100%. Okay. Do we have to do all the trig? No, what we could go through and do is say that based off of the geometry of that molecule, its symmetry associated with it, because all of those are pulling with the exact same force, it's going to come out to entirely cancel out. Which means this molecule is going to end up being nonpolar. It has polar covalent bonds, but it's nonpolar. Okay? That analysis requires understanding something about trig and angles and vectors and all of that fun stuff. Okay? Or it requires looking at it and saying that this is a symmetric molecule. Because it's symmetric, all of those poles are going to cancel out. So that when we're thinking of our dipoles, really what we need to be considering is, do we have perfect symmetry? If we have perfect symmetry, it's going to be nonpolar. Okay? If we flip back to water as an example, doesn't water have perfect symmetry? But it's polar. Is it perfect symmetry? Nope, it's not perfectly symmetric. Okay? So recognizing where all of the symmetries comes into play. This is one of the reasons why we talk about chirality and recognizing the symmetry in those relationships, because it helps us to establish relationships with dipoles and not dipoles. Kind of, sort of? Okay. The examples that we picked, admittedly, water wasn't a planar molecule necessarily, depending on your perspective. But the molecules that we picked were effectively could be drawn in a planar system. What happens if we move to something like CH4? Is that planar anymore?
No, it's tetrahedral.
That's tetrahedral. So again, we have to evaluate the shape of our molecule. And again, we could try and deal with all the trig to figure all those things out. But again, we could go through and say, do we have perfect symmetries? Recognizing the symmetry in a three-dimensional molecule becomes very challenging. But yes, we do have symmetry. Okay? Because we have that perfect symmetry, all of those being equal, everything cancels out. I don't have to worry about it. Non-polar. What happens if I put a chlorine in here? Do I have perfect symmetries? Nope, which means it's polar. Where is it polar to? It's going to pull straight towards that chlorine. Okay? Where we draw the arrow ultimately doesn't matter as long as we acknowledge the direction. Because ultimately where that arrow should be going is dropping that positive on the positive part of the molecule. Dropping it on top of the molecule can confuse things, so you'll sometimes see me draw it, okay, either to the left or to the right of the bond I'm referencing. What if I bring in another chlorine?
Still polar.
Why?
H come to C, H come to C, and C come to chloride, two-way.
Okay, and so this is going to become kind of a challenge with this. Okay, and what I'll do is modify this even more. Whoops, that's not the color I wanted. I wanted H. Is your answer still the same?
No, it's gonna cancel out two chlorine. They go to different way.
And therein lies the massive issue. You're saying the chlorines cancel out. No, they don't. This chlorine is in the plane right here. Where's this chlorine? Backwards behind the plane. So we've got something that's pulling that way and something pulling this way. Okay? Do they cancel each other a little bit? Yes, one's pulling that direction, this one's pulling this direction. So they're pulling opposites, but not perfectly opposite. And because they're pulling perfectly opposite, there will be a dipole. Okay? Which, with the red chlorine up here where I had that hydrogen, was the exact same scenario. But because of how it was drawn, we artificially interpret it incorrectly because we aren't comfortable with the three-dimensional representations. Again, this is why we do Unit 1, to try to force you to get used to those three-dimensional spaces so you don't make mistakes like this in recognizing that they're in opposite directions, so they aren't canceling out, and therefore the molecule is polar. Could I draw an arrow on this to represent where that polarity is aimed? No, okay, I wouldn't be able to, okay, at least not a nice one, because that chlorine is pulling kind of backwards, this one's pulling kind of over here. That arrow is aimed on the angle kind of going between them, going backwards. I can't draw a nice arrow on this to show that. I could attempt, but it's going to be really sketchy looking and it's not going to quite make sense. Okay? Because we aren't seeing the three-dimensional, we're looking at what appears to be a flat drawing. Does that kind of make sense? So that when we think about polarities, we have to be very, very careful to think in the three-dimensional reality, not in the two-dimensional artificial drawing. Okay? Okay. If we go back to kind of our functionality in structure, okay, the point of this was to really get us to see some of the simple chemistry. So if we looked at those three compounds, do you know the names of those three compounds? Sulfuric acid, hydrochloric acid, and sodium hydroxide. Okay? The two acids hopefully should stand out because those are acids that you've worked with before, and they have a neat little name associated with. They're called acids. Why do we name them as acids? Okay. Acid as a term implies something about the danger associated with it. So we use that term and linked the word danger with it as part of the connotation, I guess you will, behind that so we can understand some of that chemistry. Right? And so we do that because what we're trying to do is, number one, make people a little bit safer, but then it also narrows the field on some of what's happening within that particular molecule. So what do I notice that these two compounds have in common? They have a hydrogen. That's an awesome statement. Of course, what am I going to then ask? Doesn't sodium hydroxide have a hydrogen? So we could try and push hydrogen bonding. HCl does not have hydrogen bonding. Okay. The NaOH does, and H2SO4 does. What do the red ones still have in common? Looking at the hydrogens, okay. What is different about the hydrogens in the red box versus the blue box?
They can donate protons.
How do you know that? How do you know that they can donate protons? Even that language of protons is a bit sketchy if you ask me. You're not wrong. Really, you don't see anything else that the red hydrogens have in common, but the blue one does not? Really simple.
They're at the beginning of it.
Yeah, you're like, oh, this is stupid. I was just at the beginning. Yeah. Okay. In fact, that was our rule in Chem 130. We denoted acids by putting the hydrogen in front. Okay? Because we're trying to call out attention to the chemical reactivity of that hydrogen. Because what do acids do? They donate protons. Well, what the heck is a proton? Feel free. Okay. It is positive. There's lots of things. I could say cations, and I'm not saying cation, I'm saying proton. So positive, how is a cation different from a proton?
You can give away its charge.
Where do you find protons? Okay. What word am I trying to spell there? Oh my God, let's try that again. Okay. Our proton is a positive. It is the subatomic particle, okay, found in the nucleus. Okay. And how is that relevant for us? If we were talking about acids doing that, are we talking then about nuclear chemistry? Okay. Like everything that comes with that. Heisenberg, atomic bombs, explosions, that's what's happening when we have acids. I mean, they're dangerous, but they aren't that. Okay? So what's going on behind that? Well, what we can do is pull these out a little bit and we can talk about their chemistry. Okay, so let's take a look at the simpler one. Let's look at HCl. What happens to the electrons in the bond between hydrogen and chlorine? They're shared, that's why it's a line, but is it fully shared? No? Why not?
Hydrogen can only carry 2.
So why would that change anything about the sharing? Because that's 2 electrons. That looks good to me. We just had a conversation about dipoles.
Chlorine's pulling.
Yeah, chlorine's pulling electrons. Let's, just for giggles, let's do that. Except this time, let's go all in. This is no longer chlorine just pulling on kind of shared electrons. This is saying, screw you, hydrogen, I'm taking all the electrons away. Okay? So what we could do is add a curved arrow. That curved arrow is now representing the electrons moving a certain direction. We're using 2 heads on it to represent we're moving both of those electrons. What would be the resulting structures that come out of that? Okay, well, I still have the hydrogen. I still have the chlorine. The lone pairs on the chlorine didn't do anything, but what happened to the bond? Moved? Where did it move? To the chlorine. And if it moved to the chlorine only, it's no longer sharing. Can I show it as a line? Nope. What do I need to show it as?
A charge.
Just its own separate, just leave it separate,
Leave what separate?
hydrogen.
Okay, so I'm still showing them separate. What I'm asking is what happened? This line represented what? Electrons. Where did they go?
They go to chlorine,
They go to the chlorine. How do I show them?
so you add 2, one lone pair, and the hydrogen miss the electron, so positive charge.
So now both of you are jumping to the next stage, which is good. This is what we should show from that arrow pushing. Okay, the chlorine is taking those electrons. There's the chlorine with all the electrons. We got the green electron showing that arrow moved. The hydrogen has no electrons, so it's chilling by itself. If we now push on that, what happened to the chlorine? Well, the chlorine started neutral and gained electrons and is therefore negatively charged. I can also go through and say chlorine has 7 valence electrons, minus 8 is negative. There we go. All the stuff that we did in Unit 1, we're trying to now manipulate that and use that. What happened to the hydrogen? Became positive. Okay? So now what we've done is we've done a chemical reaction. We broke a sigma bond. That's cool. Okay? Whether that's allowed to happen or not becomes the next question that we would move into. Okay? Into that motion, what we could now start to do is say, well, what do we know to be true about HCl? It's a fun little A word. It's an acid. Okay? And what do acids do? You actually said the definition.
Donate proton.
Donate protons. There's that stupid proton subatomic particle again. What does this hydrogen have? Right here. Tell me everything that makes up this H+. It has a proton because it's flipping hydrogen. The only way it can be hydrogen is if it has a proton. Okay, does it have a neutron? That's harder Gen Chem question. Maybe. I don't know. Okay. Officially, no. When we look at the atomic mass for hydrogen, 1 proton, and that's it. So we think of its mass, it's just 1 because it has only 1 proton. We go up to helium, it has a mass of 4. Why? It has 2 protons. How did it get the extra 2 mass? Neutrons. Why did we need 2 neutrons? What do the protons do when they get near each other? They push away. So we need some glue to hold them together. How much glue do we need? 2 glues. They're called neutrons. That's what keeps it together. Does hydrogen need a neutron? No. The only reason we need neutrons is to glue protons. If I only have 1 proton, who cares? So no neutrons. Does it have any electrons? No, hydrogen comes in with 1 electron. That would be a neutral hydrogen. This is a positive hydrogen, which means it wants electrons. It doesn't have any electrons. So it has no electrons, no neutrons, and it has a single proton. What does HCl produce? H+. And what is H+? It's a proton. That's where the term is coming from. We're not talking about it in the subatomic sense. We're talking about the identity of the atom that is now existing. It has no electrons, no neutrons. The only thing it is a proton. So we're not talking about nuclear explosions. We're talking about just this atom just chilling off by itself, and all it is a proton. Okay? This now fits the acid definition. Okay? So your definition for an acid was a proton donor. Okay? As we just addressed, proton could be a confusing term, so we could talk about it as H+ donor or a hydrogen ion donor. All of those are fine, okay? As long as you acknowledge we're not doing anything nuclear. Okay? What do acids react with? It was a horrendously vague question. Let's go to the extreme. What's the opposite of acids? So effectively what I asked is, what's the opposite of left? And you told me straight. I mean, you're right, but I want the opposite. What's the opposite of an acid?
Base.
A base. Okay? So we know acids produce H+, so what must the bases do? They must somehow consume or accept H+. Do you know the name of any bases? Sodium hydroxide is a good classic base. So let's start with sodium hydroxide. So let's run the same kind of argument with our sodium hydroxide. What kind of bond do I have between the sodium and the hydroxide? It's an ionic bond because sodium is a metal. Cool. Okay. So this one, much more so than the HCl, we can fully say that these electrons straight up go to the oxygen. There's no questions about that. That's an ionic bond. It should do that. What do we produce? Well, the Na is still there. Does it have the electrons anymore? So what might you guess about its charge? It's positive. The oxygen is still there with that hydrogen. We still have the 2 lone pairs. What happened to the bond? That moved to the oxygen. So there's that bond. What else could I add to my reaction?
Negative charge.
And if we now think about our acids as proton donors, they are giving up H+. And we said the base is probably a proton acceptor. To be a proton acceptor, what must it do?
Need to have O or F or N.
No. Okay. By saying it must have O or F or N, you're saying it has to be doing hydrogen bonding. Hydrogen bonding is a force. We're breaking sigma bonds. This is no longer force territory. This is chemical reaction. We're breaking stuff legit. What must the base do to accept that proton?
Negative.
Well, what's a characteristic of the proton?
Positive charge.
Do things like to be charged? No, charge is bad. So how do I fix that positive charge? What do I need to give it?
Give it 1 electron.
I need to give it electrons. What does my base have?
Electron.
Electrons, conveniently in a giant negative charge. So what could I do? I could take that negative and share it with that hydrogen. What's the result? And I've now made a new chemical bond. Okay? So when we're talking about acid-base chemistry, all we're talking about is the transfer of a hydrogen from one location to another. This middle work is just to allow us to see those charges. So if we're thinking about those charges from the get-go, what could we do? Well, we could just straight up ignore all of those, and we could focus on what's chemically happening. Well, what's happening? The electrons from this bond are going to that hydrogen. The electrons between the hydrogen and the chlorine go to the chlorine, and what naturally gets produced out of it? Well, I form a new bond between the hydrogen and the oxygen. I get Cl minus chilling off, and I get Na plus. Should I have the Cl minus attached to the positive?
Yes.
No. Why not? What kind of bond would that be?
Ionic.
And what do ionic bonds do in the presence of water?
No.
They dissociate back into the ions. Okay? So what we're trying to do is explain what's happening with where the electrons are moving and how they're moving about. If we understand our dipoles, that helps to establish different partial charges. It's now a question of just moving stuff around to get those things to match. Kind of, sort of? Why did we look at HCl and not H2SO4 first?
There's 2 hydrogens.
Okay, there's a possibility. Draw H2SO4 for me.
It's hard to draw.
There we go. Okay. And as long as you acknowledge it, I'm fine with that, and we can move on from it. If we were to look at our Lewis structure for H2SO4, it's going to be a really complex one for you guys because I don't think we've talked about expanded octets, and it's not something that we need to worry about for the sake of this class. But if we go through and look at H2SO4, we've got something wicked like this. Yes, it does have 2 hydrogens. Do I need to worry about 2 hydrogens? No, I worry about one, then the other. That's it. I don't look at H2SO4 and go, oh my God, 2 hydrogens. How do all those react? I don't. I react one at a time. Okay? We're going to go through and cut hair. We cut one at a time. That's a bit extreme. Okay? But you cut sections. You don't just like put a hairdryer on top of your head and then just go whoosh and axe chop everything off. Okay? You go one piece at a time. So if we go through and look at this, what would happen in the presence of our hydroxide? The negative shares its electrons with the hydrogen. And if I drew just that, I'm now forming a bond between the oxygen and the hydrogen. How many bonds can hydrogen have?
2, 1.
Try again. Hydrogen can only have one bond, which means if I only show that one arrow, I'm breaking octet. I'd be drawing a bad product. So I have to add a second arrow. This now sets me up with this structure. Okay, and then I would also still have the OH produced off. Kind of, sort of?
And where did that red OH come from?
I just added it.
Oh, it's just like
Yep, just put it in there as a reaction. Okay, so what did H2SO4 act as? What happened to the structure of H2SO4 if we look at it as a reactant and then look at it as a product? What did it do? So if here's my reactant, what do I want to compare it to? Does this thing look most like H2O, or does it look most like this? This, okay.
Yeah.
So these two things are related to each other. These two things are related to each other. So if I want to figure out what happened, I can look at beginning to end. What changed when I look at my H2SO4 when I compare it to its conjugate, its partner on the other side of the equation? What changed to its structure?
It became charged.
Okay, you could do that. What else changed? What's the formula for this thing on the left?
It's missing hydrogen.
Too late. What's the formula for the structure on the left? What's the formula for our red box structure on the right? Okay. And if we look at these formulas, one became charged. Yes, I fully accept that. What else happened?
It's different.
How? Annie?
Missing
It's missing a hydrogen. What did it do? It had to give up that hydrogen to something else.
Yeah.
You mean it had to donate the hydrogen? What did H2SO4 act as? An acid. It donated a proton. What happened to our OH minus?
Accepted.
Which means
Base.
it's a base. Okay? We referenced the product side and we called these conjugates. Okay? That helps us to explain kind of where those differentials are. Some people will call conjugate pairs, and so they'd reference both the red things as conjugate pairs and the blue things as conjugate pairs. I prefer to use conjugates just as an identifier on the product and help me to reference it. Okay? Now the kicker, all chemical reactions can go two different directions. They can go forwards and they can go reverse. So now if we look at the product side, our HSO4 minus, to look like a reactant, must do what?
Get one hydrogen.
It has to gain a hydrogen, which means what did it act as? Good, it acted as a base. What did our H2O do to look like OH minus?
Has to give
Which means?
acid.
Bingo. Okay, so when we look across an acid-base reaction, you can tie products back to reactants and refer to them as conjugate partners, okay? And you can talk about them as their opposite. So the acid on the reactant side will become a base on the product side. Okay? And the base on the reactant side can become an acid on the product side. That gets confusing because if I say identify the acid, where do you point? Is it H2O or is it H2SO4? Okay? That's why I would say we use the word conjugate. So when I say identify the acid, where do you point? H2SO4. If I say identify the conjugate acid, where do you point? The HOH or H2O. It's fine to go either way. I'm okay with it. Does that make sense? And so when we're looking at this chemical reaction, this is supposed to be a little bit easier because it's chemistry that theoretically you've already seen in Chem 130. Okay? Depending on your instructor, you may not have spent a lot of time on acid bases, and all of those terms may just be kind of ghosting for you. Okay? Because it's right at the end of the semester for most classes, and it's big stuff. Okay? We also entered this idea of equilibrium. Right? So now what's kind of the next thing that we can add to this? Okay, well, a couple things first. We talked about some definitions. There's really only two definitions we care about, Bronsted-Lowry and Lewis. Okay, and I'll draw up our acid-base, simple acid-base experiment reaction again. There's our HCl plus our NaOH. Chemical reaction happens. HOH plus our Na plus and our Cl minus. Okay. The NaCl is ultimately an ionic bond. We almost always ignore that as kind of our counter ions, and we really keep focus only on the HOH where we actually had a legitimate change in bond connectivity. For Bronsted-Lowry, we can break this down into acids and bases. We said the acid was what? Proton donor. For the record, how many times do you think you will see the question, define acid? A lot. It will show up on your exam. If you're getting it wrong, you will probably actually lose points. Not just not gain points, lose points. Because the definition of acids and bases is critical to your understanding of organic chemistry, and I would argue to chemistry as a whole outside of this class. Okay? Which means you need to know those very, very, very well. Definition of a base. Cool. The problem with these definitions is it's now centered on a hydrogen atom. Okay? That hydrogen atom then dictates whether we have an acid-base chemical reaction or not. And so ultimately what's happening with these definitions, you can go all the way back to Arrhenius, is they're making observations on chemical reactions that we have easy access to. Okay? And as we continue to find more and more chemical reactions, we want to apply those same definitions to them. The problem with that is that very swiftly we get away from transferring of hydrogens. Okay? So somebody else went through and said, well, is there another thing I could do to focus on this? Okay? Well, when we talk about the identity of an actual structure, okay, what compound am I looking at? Okay. Am I still looking at water?
Yeah.
You just said no. Why did you say no?
The gas, hydrogen, oxygen.
Now you're saying it's hydrogen and oxygen. Okay? But you're still saying yes. Why are you saying these hydrogens are connected to that oxygen?
Because they're still in the same space. I don't know.
Are they in the same space?
No.
What defines space for you? Okay? If I put the hydrogens here, what am I looking at?
That's water.
That's water, okay. But if I put the hydrogens here, is that water anymore? Okay. And whether it's yes or no is ultimately irrelevant. What's important is that at least one person said no. What does that mean? There is ambiguity in how we're drawing this. How can I clarify this to ensure that everybody knows that I'm actually talking about water here and not OH and H? Oops, without entirely erasing it. How do I clarify this to make sure Everybody knows I'm talking about water.
You draw the bonds.
I draw the bonds. Okay? Why did this become important? Talking about the atoms wasn't clear. But as soon as I draw the bonds, doesn't matter where I place those individual atoms, that line connects them. They are now chemically linked, and I have a bond, I have a molecule. I can't look at this now and call this OH and H, because there's a bond connecting it. I might be like, why'd you draw that bond so freaking long? Like, that looks stupid. That's a separate point. It's still connected. If we look at the Arrhenius or the Bronsted-Lowry definition, it's only talking about the presence of the atom. But if we only talk about the atom, we lose a lot of meaning. Because what dictates whether we have a molecule or not isn't the presence of the atoms or even the spacing of the atoms. It's whether or not we show a line representing that bond. And what is that bond? So the definition of transferring of protons is ultimately so narrow, it doesn't allow me to apply to a broader situation. But if I shift away from protons and talk about electrons, electrons can move to make bonds. That clarifies everything. It's also going to muddy the hell out of everything as well, because what do we tend to do with our electrons? For instance, do you see the bond in the red box? Do you see the bond in that red box? That red box. Do you see the electrons there or there? Almost universally, what do we do with our electrons? We imply them. We actually don't show them.
Yeah, wrong wording, sorry.
Okay? And that becomes the challenge. Okay? For the sake of this class, we should always be explicit and show them, because it will help us be able to bridge that gap and manipulate these definitions. But what we're shifting to as a potential definition for Lewis is now saying we need to go beyond the transfer of hydrogens and talk about what happened with the electrons. So if we go back up here, what did HCl do to look at Cl minus? It had to donate the proton. What did it donate the proton to? What do acids donate protons to? What did the base have to accept that proton? What charge was the proton? What did the base have to accept that proton? And what makes a negative charge? So our base, when we shift to thinking about electrons, is doing what?
Accepting electrons. No. Opposite.
What did it do? Yeah, the opposite. The base is an electron, I don't know why I pluralized it, is an electron donor. So when we go through and look at NaOH, we can split that into the ions, Na plus and OH minus. What did the Na plus do? Good answer, nothing. What does the OH minus do? Share what? Electrons. Okay? And another word for share is donate. What must the acid then do? It is now an electron acceptor. So we end up flipping the script a little bit. Okay, that flip in the script allows the definition of Lewis to apply now to almost all chemical reactions. Acids and bases as a chemical definition, Bronsted-Lowry acid and base as a definition, apply to maybe 10%, 20% of chemical reactions. Okay? Lewis, shifting it to looking at electrons, now applies to 90% of chemical reactions. So the Lewis definition is much broader and allows me to grab a hold of a whole lot more chemistry, which is why when people typically talk about organic chemistry, you'll hear them reference Lewis acids and bases far more often than they'll reference Bronsted-Lowry. Okay? And it is important to go through and acknowledge that. In that same breath, I'm going to go through and say the Lewis acid-base definition is too broad. Okay? It doesn't allow me to differentiate the transfer of hydrogens versus the transfer of just electrons. And since I already have that Bronsted-Lowry definition, okay, I want to be able to use that simultaneously. So what this class is going to do, for a couple reasons, usually, or I would argue it's just for clarity, we're going to not use the Lewis acid-base definition. Okay? Which means we have to get rid of that acid in that base term, and we'll have to introduce a different term to represent those. Okay? An electron acceptor, okay? If it is an electron acceptor, what is its characteristic? Actually, let's switch that up. Okay? If it is an electron acceptor, it likes electrons, right? If someone is a discophile, what does that mean? That might be too archaic of a term. Cool, I'm actually not positive about it. I think it's like they actually like physical records. Okay? There's other files I can come up with, but that's the problem. But the file, they like things. Okay? If it is an electron acceptor, it likes electrons. So what could be a nice word to use that brings in all the fancy Greek breakdown? We will call it an electrophile, because it likes electrons. Okay? An electron donor. Okay? We still want to use this file aspect behind this. What is it donating electrons to? Okay, so you guys both gave us two definitions, which is fun. The electron donor means it itself was negative. There's your part. But what is it liking? What does it want to give those electrons to? Protons. Where are protons found? So we will use the terms electrophiles and nucleophiles to reference an atom's individual ability to accept or donate electrons. And of course, I've lost connectivity. That's lovely. Freaking network. Okay. Why has that become important to us? Well, the reason why I like doing that is now I can still keep the acid-base definition. And in the acid-base definition, we're talking about protons, so the transfer of hydrogens. Okay? But now I don't have to call this Bronsted-Lowry acids or Bronsted-Lowry bases. I can just straight up say acids and bases. The Bronsted-Lowry is now implied within that name because and that's why the nucleophile didn't drop down there. We'll see if it actually connects. Something with the network went weird, which means the iPad and the computer are not talking to each other. Right? But that says nucleophile. Kind of makes sense? Okay. And this will, I guess, just kind of suck for everybody else because the recording is going to fail here. But I will attempt